In this video, we will learn how to balance chemical reactions. Every chemical reaction must be balanced, which means that there has to be the same number of each element on both the reactant side and on the product side. For example, in the reaction below, we are reacting hydrogen with oxygen to produce water. And that means we have to have the same number of atoms of hydrogen on the left and on the right, and the same number of atoms of oxygen on the left and on the right. So I do recommend keeping track of each atom as you are going along. So right now I'm going to look at hydrogen and then at oxygen on both sides of the equation. And on the left, we can see that we have two hydrogens. On the left, we also have two oxygens. On the right side of the equation, however, we have two hydrogens, which is good, right? We have both two on the left and two on the right. But then we have a problem with oxygens, because right now there is nothing listed after oxygen, which really means that the subscript is 1. And that means that we have one oxygen. And that's a problem because if we have two oxygens on the left, we have to have two oxygens on the right. And the only way to fix that is to use a coefficient in front of the formula. We can't change the subscript. We can't just take this number and multiply that by 2, because then we change the identity of the substance entirely. So what we're going to do is multiply water over here by 2 to fix that, because this is now going to multiply our oxygen by 2. And now we have two oxygens on the right. The problem with that is that we are also multiplying hydrogen by 2, right? We are multiplying this entire formula by 2. So when we multiply the hydrogen, we now have 4 hydrogens. And that means that this messes up our ratio on the left side of the equation, because now we have 2 hydrogens on the left and 4 hydrogens on the right. But we can fix that. What we can do is multiply hydrogen by 2 as well. And if we do that, then this gets multiplied, and we end up with 4 hydrogens on the left. So this means that now we have 2 hydrogens on the left, 2 hydrogen molecules on the left, which gives us 4 hydrogen atoms. We have 4 hydrogen atoms on the right. Then we have 2 oxygen atoms on the left and 2 oxygen atoms on the right. This is now a balanced chemical equation where we have the same number on either side of the equation. So I do want to be clear about some of the terminology here. Let me erase the highlighting. Okay, so the numbers that I am writing in front of the formula, the ones that I am highlighting in yellow, those are what we call coefficients. Maybe I should do that in blue. So the big numbers in front, those are coefficients. And coefficients must be whole numbers. So we can't have decimals, we can't have fractions, they have to be nice whole numbers. And everything gets multiplied by the coefficient. So the entire formula gets multiplied by the coefficient. The little numbers that I am highlighting in pink, those are what we call subscripts. And subscripts tell us how much of each atom is present in the formula. We cannot change the subscript. So cannot change subscript. And I will highlight that. You can change the coefficient. We can definitely play around with that. We can multiply things by different numbers, totally fine. We cannot change the subscript, because if we do that, we change the chemical formula, which means we are entirely changing the identity of the substance. So for example, if we write H2O, that means water. If we change that subscript of 1 here to 2 and we write H2O2, this is hydrogen peroxide. And that is an entirely different type of compound. Water you can definitely drink, and you should. Hydrogen peroxide you do not want to drink. Completely different compound, it behaves differently. So you never want to change the subscript, you only want to change the coefficient. And let's talk in a little more detail about what this means. So everything in here right now, the fact that we are multiplying this entire molecule by 2 means that we have 2 H2 molecules present in this reaction. Because there's nothing out front here, that means it's a coefficient of 1. That means that we have 1 oxygen molecule. On the right-hand side, we're multiplying the entire water molecule by 2, which means that we are producing 2 water molecules. So that's what these coefficients mean. We're reacting 2 hydrogens with 1 oxygen to produce 2 water molecules. We could also do this with atoms. So these are all referring to molecules on both sides. We could do this with atoms. We're multiplying 2 hydrogen atoms by 2. So this really means that we have 4 hydrogen atoms reacting with 2 oxygen atoms to produce 2 times 2, 4 hydrogens. And there is no subscript after oxygen here, which really means the subscript is 1. So this is 2 times 1, 2 oxygens. And now we can see how everything balances out. We have 2 oxygens on the left, 2 oxygens on the right, 4 hydrogens on the left, and 4 hydrogens on the right. Now, of course, the way that we have this written would take a very long time, so we will learn some shortcuts on how to do that. Let's take a look at this reaction. So here we'll go through and identify how much of each atom we have on the left and on the right, and then we'll go from there. So it helps to kind of write yourself a little table and keep track, and maybe I'll do it vertically. Okay, so on the left right now, we have 2 iron atoms, and on the right, we have 1. So right off the bat, we can tell that this reaction is not balanced. We're going to have to fix that. On the left, we have 3 sulfurs, and on the right, we have 1 sulfur. So that is also not balanced. We'll have to fix that as well. On the left, we have 1 hydrogen, and on the right, we have 2 hydrogens. And on the left, we have 1 chlorine. And on the right, we have 3 chlorides. Okay, so we'll definitely have to fix some stuff here, and we're going to have to use coefficients to do that. So right now, we have 2 irons on the left and 1 on the right. So the way that I'm going to fix that is by multiplying this entire formula by 2, which means that everything in here gets multiplied by 2. So the iron gets multiplied by 2, the chloride gets multiplied by 2. So now we have 2 irons on the right and 6 chlorides on the right. This also messes up our chloride here because now we have 1 chloride on the right and 1 chloride on the left and 6 on the right. So I'm going to multiply this entire formula by 6 to fix that. So that means the chloride gets multiplied by 6. The hydrogen gets multiplied by 6. So now we have 6 hydrogens on the left and only 2 on the right, which means we have to fix that. And the way that we're going to do that is by multiplying this formula by 3. So now the hydrogen gets multiplied by 3, which gives us 6 hydrogens. And the sulfur gets multiplied by 3, which gives us 3 sulfides. And now I'm going to go back and check if everything checks out here. So 2 irons on the left, 2 irons on the right, 3 sulfurs on the left, and 3 sulfurs on the right. So 3 times 1, that checks out. Then we have 6 hydrogens on the left, 6 hydrogens on the right, and 6 chlorides on the left, and that's coming from the coefficient here. So we're getting 6 times 1, 6 chlorides, and 6 chlorides on the right, which comes from the 2 in the coefficient times the 3 in the subscript. This now checks out, and that is our balanced chemical equation. So balancing chemical equations is really a trial and error sort of thing, where you're going to look at each atom individually. You're going to multiply by a coefficient until that checks out. However, there are a few tricks that you can use to make this process a bit more efficient. So let's take a look at this when you have polyatomic ions. So balancing equations that involve a polyatomic. And here is an example. So let's say that we have sodium phosphate reacting with magnesium chloride to produce magnesium phosphate and sodium chloride. The easiest and most efficient way to do this is to keep the polyatomic as a whole unit. So keep polyatomic as a whole unit, which means we're not going to treat each atom individually because that would take a really long time. So if you separate sodium and phosphorus and oxygen and magnesium and chlorine and you look at all of them individually, it will take a really long time. So it's best to just keep everything as a whole unit. And I could say on the left, I have 1 phosphate. Notice that that phosphate is not in parentheses. We don't have a subscript after it indicating that this is being multiplied by anything. So we have 1 phosphate on the left and 2 phosphates on the right. Notice there's a coefficient of 2 after it. It is multiplying that phosphate. So right off the bat, we know that this is not balanced. So we are going to have to fix that. And what we could do is, well, we see that we have 2 phosphates on the right, 1 on the left. So I'm just going to go ahead and multiply that by a coefficient of 2. We see that now this is going to edit our sodium because we started off with 3 sodiums on the left, but we have to multiply that by 2. So when you do that, you're really doing 2 times 3, which means you have 6 sodiums on the left. And on the right-hand side of the equation, there's 1 sodium. There's no subscript indicating that this is a multiple of anything, so that is 1 sodium atom. Well, if we want to turn that into 6 of them, we're going to have to put a coefficient of 6 in the front. And that is also going to multiply the chloride. Now we have 6 chlorides on the right. If we look at the left side of the equation, we see that here we have 2 chlorides. So if we have 2 of them on the left and 6 of them on the right, well, that means that we have to multiply the magnesium chloride equation on the left by 3, because that is going to give us 3 times 2, 6 chlorides. And the only thing I have not looked at is magnesium. And magnesium, right now we have 3 of them on the left because we multiplied that by 3. And we have 3 of them on the right, so that actually solved that problem, and we are now finished. And you can always, and I encourage you to always go back and check and make sure that this is all the way that it should be. So right now we have 6 sodiums on the left, 2 times 3, 6 sodiums on the right, so that checks out. We have 3 times 2, 6 chlorides on the left, and 6 times 1, 6 chlorides on the right. That checks out. 3 magnesiums on the left, 3 magnesiums on the right, and then we have 2 times 1, 2 phosphates on the left, and 2 phosphates on the right. And you can see how keeping the polyatomic as a whole unit makes this process a little bit faster than if you were to do this for every individual atom. There is another variation of the polyatomic that you could see. I'll show you an example of that right now. So let's say we had calcium hydroxide reacting with, this is phosphoric acid, and we'll cover acid naming in a different video. To produce calcium phosphate and water. Whenever you get into a scenario where you have an OH on the left and water on the right, rewrite water as HOH because it will make the balancing a lot easier. So notice you have a hydroxide on the left and H2O on the right. What I'm going to do is I can even erase that and I will rewrite it as HOH because that will make the process a lot easier. Now I can treat this as a polyatomic and notice how you have 2 hydroxides on the left and only 1 on the right, which means I'm going to have to fix that by multiplying this by 2. And now we can treat this as a polyatomic rather than looking at every individual atom that is present in the formulas. This also changes the amount of hydrogen, and it looks like 2 will actually not work out here because this gives me 2 hydrogens here and 3 hydrogens here. So I'm actually going to start with a different atom. And this is also how you can tell this is a little bit of a trial and error sort of deal. So here I have 1 calcium on the left and 3 calciums on the right. So I am going to fix that by multiplying this entire formula by 3. And that looks like it's going to take care of the hydrogen problem that we had. Alrighty, so this now gives us 3 calciums on the left, 3 calciums on the right. That is fixed. But now it gives us 3 times 2, 6 hydroxides on the left, and we only have 1 on the right. So what I'm going to do is multiply this entire formula by 6, and now I have 6 hydroxides and also 6 hydrogens. Notice on the left we only have 3 hydrogens. So I'm going to fix that by multiplying that by 2. And now we have 2 times 3 hydrogens. That gives us 6 hydrogens. And we also have 2 times 1, 2 phosphates. And notice that on the right, we have 2 phosphates. So that actually ends up fixing everything, and this equation is now balanced. There is one more challenge that will arise, and that is balancing combustion reactions. So combustion reactions, incredibly easy to predict the products, pretty difficult to balance them. So just as a reminder, combustions will always have the same format. So here is an example. We will have some kind of hydrocarbon, and this is a hydrocarbon because it has carbon and hydrogen only. It will always react with oxygen gas, and it will always produce carbon dioxide and water. So predicting the products, incredibly easy. They are always the same. Balancing them, however, can be a little bit tricky. So the guidelines that I recommend is start with carbon, Then balance hydrogen and leave oxygen for last. If you start with oxygen, this will become really painful and it will turn into a mess. Leave oxygen until the very last. And the reason for that is that you're starting off with oxygen in one reactant, but oxygen appears in two different products. And it ends up creating a lot of chaos if you start off by trying to balance that. So leave it as last. The other thing that you can do, and this will come in handy in a lot of scenarios, is that you can use a fractional coefficient to make balancing easier. And then multiply to get rid of the fraction. So let's see what I mean by that. Let's use these guidelines to balance this chemical equation. We have 6 carbons on the left and only 1 carbon on the right. So in order to fix that, I'm going to have to multiply this entire equation by 6. That takes care of my carbon, right? Now I have 6 carbons on the left, 6 on the right. We are good to go. I'll deal with hydrogen next. We have 6 hydrogens on the left and 2 on the right. So to turn that into 6 hydrogens, I'm going to have to multiply that by 3. That now takes care of the hydrogen. Cool. Now we want to deal with oxygen, and this is where things are going to get a little bit more challenging. So if we look at the carbon dioxide example, we have 6 times 2 oxygens, which means that we have 12 oxygens in this formula. If we look at the water, we have 3 times 1 oxygen, so that is giving us 3 oxygens. And that means that on the right side of the equation, we have 12 plus 3, 15 oxygens on the product side. And this becomes challenging because on the right, we now have an odd number of oxygens, but on the left, we only have 2 oxygens. And there's really no simple way to turn an even number into an odd number. And the way that we could do that, so if we wanted to turn 2 into 15, well, we could use a fractional coefficient. We could multiply this by 15 halves. And then the 2's would cancel out, and we would get 15 is equal to 15. So the only simple shortcut way that we can deal with that is by using a fractional coefficient of 15 halves. And this is saying that the 2 over here in the numerator is going to cancel out the 2 in the denominator, and we are getting 15 oxygens on the left and 15 oxygens on the right. So that is the quick way that you can balance this equation. Now the problem is that we have 15 halves as a coefficient. And we said the coefficient has to be a nice whole number. It can't be a fraction because 15 halves of an oxygen molecule doesn't really make sense chemically. You can't have half of a molecule. So we have to get rid of that fraction. And the way that we can do that is by multiplying the entire equation by 2. Because if we multiply this by 2, then the 2 over here is going to cancel out the 2 in the denominator, and we will just be left with 15. But of course, anything that we do to one formula, we have to do to every formula. So that means that C6H6 is going to get multiplied by 2. Then our oxygen gets multiplied by 2. And well, when 15 halves gets multiplied by 2, we end up with 15. Then we end up with CO2. And of course, the 6 in the coefficient here also has to get multiplied by 2. So we end up with 12. And then the water has to get multiplied by 2. And we had a coefficient of 3 in the front here. When that gets multiplied by 2, we end up with 6 waters. And this is now the correct balanced chemical equation where everything will check out. And I encourage you to go back and look at each atom individually and prove to yourself that this is the correct balanced chemical equation. So with combustion reactions, the coefficients can get quite large. If you see something like 25 oxygens, don't be alarmed. They can be pretty weird numbers because of that. So in order to get the fractional coefficient, your denominator will always be 2 because that comes from the subscript of oxygen. The only thing that's going to change is the numerator, and the numerator will be equal to whatever number of oxygens you are trying to get from the right side of the equation. And then at the very end, you will multiply that entire thing by 2 to get rid of the fraction. And that is a pretty quick way of balancing combustion reactions.